For as long as we have had eyes to look up, the moon has been our clock and our compass, our nightlight and our omen. It pulls the oceans like a giant hidden hand, lifts silver from black water, and sets a rhythm that every coastline learns by heart. It feels eternal, unchanged, unchanging. But the quiet truth is that the moon is slipping away from us. Not falling, not fleeing, drifting. Year by year, about 3.8 centimeters at a time, Earth's only natural satellite is moving outward, and that almost invisible recession is already rewriting the future of this planet. You cannot see it with your eyes, yet we measure it with light. During the Apollo era, astronauts left retroreflectors, small mirrored panels, on the lunar surface. From Earth, scientists fire lasers at them and time the echo. The round trip grows longer by tiny, merciless increments. The distance increases. The story of Earth and Moon is changing its ending. The reason sits in the tides. The Moon's gravity raises two bulges in our oceans, one facing the Moon, one facing away. Because Earth spins faster than the Moon orbits, those bulges are dragged slightly ahead of the Earth-Moon line. Water pulls on rock. Rock pulls back on the Moon. That friction robs our planet of rotational energy and passes it to the Moon's orbit. Earth's spin slows. Our days lengthen. The Moon gains orbital energy. Its orbit grows. Long before cities and ships and myths, a terrestrial day lasted about 18 hours. Hundreds of millions of years later, it stretched past 22. Now it is 24. In the deep future, it will be longer still. If you could stack the shadows of sunsets on the wall of time, you would see the spaces between them widen, like a heartbeat that's learning to slow down. But the moon is not only a clock you can measure. It is a lock you can feel. The same tidal forces that shape our seas have synchronized the moon's rotation. It keeps one face toward us, always. That is why for all of human history, half of the moon never rose or set over our horizons. The far side was rumor and imagination until 1959, when the Soviet probe Luna 3 curved behind the lunar limb and photographed a landscape that did not match our expectations. On the near side, we see dark basaltic maria, ancient lava plains that our eyes read as a human face. On the far side, those seas are rare. Instead, it is a battered world of highlands, an old face heavy with craters and scars. Why so different? Theories suggest the far side's crust is thicker, a quirk of how the newborn moon radiated heat. Perhaps the near side cooled under Earth's warm glow and stayed thinner, letting lava well up, while the far side sealed early beneath a deeper shell of anorthosite. Gravity maps from NASA's Grail mission later revealed dense mass concentrations, mascons, beneath some basins, hints of ancient impacts and frozen seas of magma. The far side is not a mirror image. It is a separate history, and there are stranger clues. At the lunar South Pole yawns the South Pole Aitken Basin, one of the largest impact structures in the solar system, so deep that it may expose material from the moon's mantle. In craters near both poles, sunlight never rises. Temperatures fall below anything you can imagine. There, in permanent shadow, instruments have detected water ice, molecules trapped for eons in darkness, preserved like whispers in a vault of cold. China's Chang'e 4 became the first mission to land on the far side, using a relay satellite parked beyond the moon to talk to Earth. The far side is radio silent, shielded from our electromagnetic noise. Strange magnetic anomalies distort compasses there. Some regions reflect radar in ways that hint at buried roughness or exotic chemistry. We have mapped, sampled, bounced signals, and walked. Yet the moon keeps a private vocabulary of secrets, and it only teaches us one word at a time. Still, the grand trend does not wait for our understanding. The moon goes on drifting outward. What does that mean for us? First, the tides will shrink. Not tomorrow, not in your lifetime, but steadily, like wind laid down by evening. Coastal worlds that depend on strong tidal exchange, wetlands, mangroves, spawning grounds, will weaken. The ocean's great conveyors, powered in part by tidal stirring, will shift their balance. Weather patterns will adjust. The change will be slow enough to hide inside centuries and fast enough to matter across ages. Second, the moon's stabilizing effect on Earth's axial tilt will relax. Today, our axis leans about 23.5 degrees, and the moon's gravity helps keep that tilt from wobbling wildly. As the moon recedes, the stabilizing torque weakens. The exact outcomes depend on complex resonances with the sun and planets. But the risk is simple to state. More variation, more climatic swing, more seasons that are not like the ones we inherited. There is a deadline you can mark, though you will not meet it. Total solar eclipses. Right now, by cosmic accident, the moon and the sun are almost the same apparent size in our sky. That is why the moon can perfectly cover the sun, turning noon into midnight in a corridor of shadow that races across continents and makes millions weep. But as the moon recedes, its apparent diameter will shrink. In about 600 million years, totality ends forever. The best we, or our distant heirs, will ever see after that is an annular ring of fire, a bright halo around a disk too small to hold the light. Eclipses will still happen, but the perfection will be gone, and with it a particular kind of human astonishment. Imagine standing in that future, holding a memory you never lived, wishing for darkness that will never fall again. How far can this go? The long mathematics of tidal evolution says that if nothing else intervenes, Earth and Moon will creep toward a double lock, one rotation of Earth per one lunar month. Day and month matching, both faces fixed. But if nothing else intervenes is a fantasy clause. Long before tidal evolution can finish its slow dance, the sun will change the music. In about 5 billion years, the sun will swell into a red giant. Its outer layers will drag on planetary orbits, its light will scorch and then wash over the inner system, and whatever happens to Earth, scorched, swallowed, or spared, it will not be the world we know. The fate of the moon in that far fire is uncertain, but this we can say. Predictions that claim the moon will calmly drift free on a quiet night presume a sun that never ages. Ours does, and it will. The moon's ultimate end will be written in solar flame, not in laser echoes. What about the question everyone asks? Do we truly know what's on the other side? We know far more than we used to, and yet the far side still earns its name. It is far, radio quiet, and difficult to reach. We have global maps, gravity fields, mineral fingerprints, and a handful of landing sites. We suspect pockets of water ice in polar cold traps. We can point to curious magnetic patches and odd reflectivity near some craters. We have measured the crust's thickness and found it lopsided. We even dream of building a radio telescope nestled inside a far-side crater, shielded from Earth's chatter, to listen to the universe's first light. But the moon is no museum exhibit. It is a world. You cannot understand a world with flyovers and a few shovelfuls. That is why Artemis and future missions matter. To sample the polar ice, rocket fuel, air, science fossilized in frost. To drill the far side's crust. To test what we only infer. Every footprint we place up there will step on a mystery. And if the moon keeps receding, what will a night look like in the far tomorrow? The moon will sit smaller, colder, higher. The shadows it casts will soften. The tides will whisper instead of roar. Children will learn eclipse from archives. Navigators will trust stars more than sea. The stories we tell will change, because the sky that raised our myths will raise different ones. Yet the moon will still be ours in a way that distance cannot erase. After all, we carry pieces of it in our hands. Lunar meteorites in deserts, dust in a handful of glass beads returned by robots and humans, and more strangely, in our bones. The calcium in you was forged in stars. The rhythms in you were trained by a light that bled from a sun and bounced from a gray rock born from Earth's own torn flesh. You cannot fully separate Earth from Moon without separating the past from the present. They made each other. They still do. So when someone asks, how do we know it's drifting? You can answer with lasers and mathematics, with Apollo reflectors and tide charts, and day length stitched into coral growth rings. When they ask, what's on the far side? You can describe a high-crusted wilderness, radio quiet, crater-rich, hoarding ice and secrets. And you can admit that we don't know enough. That not knowing is the point of going. When they ask, what happens when it's gone? You can say that long before any goodbye, the sun will rewrite the script. That what really changes for us is not a sudden loss, but a slow loosening. Gentler tides, longer days, a tilt that may wander more, eclipses that lose their dark. And when they ask, how long? You can give them 2 clocks, hundreds of millions of years to the last totality, billions to solar metamorphosis, countless quiet nights between where the moon is still up there, a little farther than yesterday, a little nearer than forever. Look up tonight. The moon is not moving fast, but it is moving. The universe almost never shouts. It prefers to rearrange our lives with whispers. A centimeter here, a second there, a shadow's edge that doesn't quite fall where it used to. That is how worlds change. That is how endings begin. And if, in some age beyond ours, the moon passes another world and lends it tides and stories and songs, perhaps something will crawl from a warm, shallow sea and look up and feel what we felt. Perhaps the universe does not lose things, it only passes them along. If so, the moon is not leaving us. It is carrying us forward, the mark of our oceans and our eyes and our grief, into someone else's sky.